Welcome back. Here's a voltage division problem with load effect. Okay, so let's refer back to the notes from chapter 3. We have a voltage divider here, right? And this voltage division equation here applies when we have an open circuit here. But what's typically done is there's a load resistor put across these terminals, and that will affect the voltage. So as long as the load is much bigger than either one of these divider resistors, this approximation will hold. Okay, but if this load resistor is close to these values, it'll start to affect the sort of ideal open circuit situation, right? So if you're using a voltage divider as a primitive voltage source, you have to make sure that the load is much bigger than these two guys. If it's not, it's going to start throwing off this approximation. Okay, so we'll work that's what this is about. And we'll work this in a little bit more detail. But here we're given that as I'll talk through that concept a little bit more as I work the problem. So here's a 18 volt ideal voltage source, and it's connected to a 40 ohm resistor and an unknown value R2, but we know that the open circuit voltage across R2, this V0, is 6 volts. Okay, so this is open circuit. In other words, R sub load is infinity. Okay, so we're asked to find what is R sub L for V0 equals 4 volts. So right now with an open circuit, that is an infinite resistance on the load, we have 6 volts. But if we put a load in here, what does that load have to be to start to draw this down to 4 amps, which is quite a lot of drop. That's like two thirds, right? It's like 2/3 is, a big drop for these kinds of. It can be in certain circumstances. Depends on what you're doing. Okay, let me just re-say. So there's right now with an open circuit, there's 6 volts. We want to put a load in there that's a particular resistor value that's not infinite, and such that we get a 4 volt thing in there. So first of all, let's solve for R2 since it's not given. Okay, so voltage division. We can solve for we can get R2. So the voltage division equation, V0 is V source over some resistors, right? So 6, is V0 is given by this 18 volts being dropped over 40 plus R2, and then when you put on the top, you put R2, right? So the source voltage, 18 volts, is divided by, the sum of the resistors and then the adjacent resistor on the top. And so I'm just applying voltage division, but the unknown here is R2. Okay, so this we could solve the algebra on this, and what do we do here? We move the denominator over to the other side. So 18R2 equals 6 times R2 plus 40 is the algebra. So we can multiply this R2 or the 6 into this stuff and then move it back to the other side, and you end up with 12R2 is 240, right? And so R2 is 20 ohms. Okay, so a 20 ohm resistor will give you 6 volts drop here. Does that make sense? This is This is 18 volts, and we have 40 volts and 6 volts, which is a sorry, I mixed up voltage and resistor. We've got so resistor value is 40 here and 20, right? This resistor is 40 ohms, and this resistor we just solved is 20 ohms. That's 2 to 1. And the voltages, do they match? So this is going to be 6 volts, and it has to sum to 18 volts. So there must be 12, right? Because 18 minus 6 is 12. So there has to be 12 volts across here and 6 volts across here, because 12 plus 6 equals 18. And then 12 and 6 is a 2 to 1 ratio, right? 12 volts and 6 volts is a 2 to 1 ratio, which matches the 40 ohms and 20 ohms 2 to 1 ratio. So it is checking out. All right. Okay, now we want to add in or connect, I'll say, just to be clear, connect some load R sub L to A, B terminals to get V0 equals 4 volts. So what we're gonna do is, I'm gonna scribble it over here in the corner kind of tiny, but we're gonna do this. The 40 is gonna still be here, the 20 is gonna be here, and then what we're gonna do is we're gonna hook up R sub L here, and we want this to be 4 volts across here. So the trick to this problem is realizing that we can simplify this with something, let's call it R equivalent. So that's what I'm going to draw here a little bit bigger. So we have this 18 volts, then we have the 40 volts, and then we have the R equivalent. R equivalent, and across terminals A, B. So what's really happening is I've hooked up an additional resistor R sub L across AB, but those two resistors in parallel, the 20 ohm and our new R sub L resistor, they're in parallel, and I'm just calling them R equivalent, okay? And there's going to be 4 volts across this, plus to minus. So we can use our voltage division equation again on this new circuit, and basically this 4 volts here comes from 18 volts getting dropped across some of these guys, R equivalent plus 40 over R equivalent, or the other way around, but what I wrote right here, I think I said it backwards, but this, and right, because we're dividing 18 volts by this ratio of resistors, and it's the sum of the resistors on the bottom, and then it's the adjacent resistor on the numerator. So you could do some algebra steps, but you're going to end up with R equivalent is 11.43 ohms. Okay, then we can go back to this dude, because we know that this is 20 and we know R equivalent, so we can solve for the unknown because we have a formula for parallel resistors. So R equivalent is 11.43. It's given by R2 RL over R2 plus RL, right? This is our formula for resistors in parallel. The 20, R2 is the 20, and RL is unknown. And those should sum up the parallel equivalent to 11.43. So let's just solve for RL, and I'll do the algebra. I'll do the algebra. So it's 11.43 is 20 RL over 20 plus RL. So 20 RL equals 11.43 times RL plus 20, right? Just moving that guy over there, and then 20 RL minus 11.43 RL equals 20 times 11.43, and therefore RL is this thing here is going to be 228.6, and then factoring out the 20 and subtracting out the R sub L, and then subtracting 11.43 from 20, end up with 8.57, and that's going to be 26.67 ohms. That's the new value of RL. And so the last thing we could do, and I ran out of paper, but we could redraw the full circuit with this new value in here. Remember, we're simplifying. We did this. This is the final circuit with an unknown RL value, and then we simplified this with R equivalent. Then we used voltage division to get R equivalent, and then we broke R equivalent back up into two parallel resistors using the parallel resistor formula. But let's just, the final circuit, let's draw that. The final circuit's going to be, just to be clear, the final circuit, the 40 guys sitting here, and this 20 guys sitting here, and then we across terminals A, B, and then we hooked up this guy. We hooked up a 26.67 ohm resistor. Okay. The net result of this is that this appears to be an 11.43 ohm, R equivalent, and you end up with 4 volts across here. All right. What are they asking for? The RL for V0 equals 4 volts. This is the answer. Good problem. It's starting out with a voltage divider that has a 6 volt on this branch with an open circuit, and then when you hook up a load to it, it changes this division problem, right? Basically that's it.